Hello, welcome to Physics World. This is Mrs. Homberg. Part of continuing our analysis of circuits is to start working with circuits that go beyond series and parallel basic circuits. We're going to start the very simplest of compound circuits. Let's analyze the very most basic and simple of compound circuits. Compound circuits are circuits which include some series and parallel components. We see two versions of these very basic compound circuits. One has a battery, a single resistor on its own, and then a branched portion which is clearly parallel. The other simple compound circuit is one where we immediately encounter a parallel portion and then there is a single resistor after that. What happens is we have to note where I battery is the same as the current through a particular resistor. If we call the current out of the battery I bat or I total, could be seen either way, you see that there is only one path for the current. So we're going to notice that I1 equals I battery. This is a river of current, which at node A will break up into I2 and to I3. And when I2 and I3 meet at this juncture B, they will resume, add up to I battery again. How is this circuit different? This circuit shows us that we will again have I battery coming out of the high potential end of our battery, but at node A now, it immediately splits into I1 and I2. When those two currents again meet at node B, they will come out and they will add up to I3, which equals I battery again. Notice that I battery must continue and go back into the battery at that point. So this is where Kirchhoff's circuit law is very important for us. We notice that the before is the I total, I battery here, and breaks up into smaller currents here, and they add up to the total again later. Here we see an immediate split, and they will add up again to make I3 equal to the whole I battery. What else should we notice? We should try to notice where the voltages are the same as the V battery and 0 volts. Well, let's start off with marking our high potentials and marking low potential. With this in mind in our coloring as a guide, we know that anywhere along pink is the same voltage as the battery. We're going to call that V high here, but if we had a number like 100 volts, we would put 100 volts there. This is the 0 volt end, so now we can put 0 volts here and 0 volts there. So we know that if we could calculate the voltage drop across here with I1 or I battery and that resistance, we could go from V high to this new voltage here. If we know that this is whatever V high voltage this is, we would put V high here and V high here. This will help us when we find out and realize that this is 0 volts. We can calculate the voltage drop across R3, and then that will allow us to determine if this is 0 and that's the voltage drop there. We can figure out what all of these wires' voltage is. Hi, this is Mrs. Homberg, and we're going to do the analysis of our first simple compound circuit. First things first, let's color in our voltages. We should have anything attached to the high potential 12 volt end of that battery marked as 12 volts. Well, hopefully you filled in the voltage colors to match mine. And when you see that now, let's go through and see what we learned from our compound circuit rules. We know that I battery goes right out of the high potential end of the battery. We know that I1 is going to equal I battery because it has only one path. We know there's going to be a voltage drop here because we multiply I1 times R1. We're going to calculate that. And then, of course, we'll end up knowing what the voltage is all along the orange wires. But for now, we know this is 0 volts, so we can mark this is 0 volts and this is 0 volts. We now have all the information we possibly could write down just from seeing the circuit. Our first step is always to find the equivalent resistance of the circuit. Well, we see orange to blue. We know that we can get an equivalent resistance for those two. If we go and do our math, which follows along with parallel circuits rules, we see that 1 over R23 equals 1 over 4 plus 1 over 12. And in order to get R23, we need to get the reciprocal. R23 is 3 ohms. So we could technically replace R23 with 3 ohms. We now see that this looks a lot like a series circuit. Now you see the definition of series and compound, a series and parallel making a compound circuit. We now know that by removing the parallel piece, we've made this look like a series circuit. So we could now calculate our series part, and that would end up being REQ. R1 plus R23 will give us R equivalent. R equivalent comes out to 6 ohms, and we can immediately fill our table. Now what should we do? Well, we've got to get our I total, I battery. So let's start with that calculation. I battery, or I total, is part of the Ohm's law equation that's going to include the voltage of the battery, the current of the battery, and REQ. And when we do that math, we'll get 2 amperes. We're going to put that right here. We've drawn this I battery. We know that it is 2 amperes. So because of our discussion earlier, we know that that current is going to go right through R1. We can now use this information and say, oh, I1 is the same as I battery. There's a single path for the I battery to follow. I'm going to fill in I1 on the table. 1 equals 2 amperes. By filling that in, I can also get the voltage across R1. I use my Ohm's law again, and I find that that is 6 volts. I can then mark this as a 6-volt drop. So if this is 12 volts, because it's connected to the high potential end of the battery, and I know that current going through this resistor is going to cause a 6-volt drop, 12 minus 6 means there's 6 volts left over here. Now we need to resume looking at our circuit with all its components uncovered. We will notice that R2 and R3 are in parallel. Well, what does that mean for voltage? Well, we said that when things are in parallel, they're going to have that same color before and after, orange and blue, orange and blue. Well, if this is 6 volts for orange, that means this is 6 volts and this is 6 volts. 6 volts down to 0 means the drop across this and the drop across this must be 6 volts. I can fill that in right away in our table. Okay, they're in parallel. I can do my calculations and I will notice that they are no longer unknown voltages. Well, if I know those voltages, I can then use Ohm's law to calculate I2 and I3. So I2 comes out to 1.5 amperes and I3 comes out to 0.5 amperes. So my whole table is filled in. How can I check my answers? Well, we're going to call this node A, and we know that we can check currents using Kirchhoff's circuit law. Using Kirchhoff's circuit law, we know that at A, all the currents in must equal all the currents out. 2 amperes in must equal 1.5 plus 0.5. They check out.